Human ingenuity has changed our lives in incredible ways. And the pace of change seems to be quickening all the time. But for all that, we rarely consider the little miracles embodied in the simple objects which fill our lives. So what marvels of manufacturing do everyday products conceal? Salt, running shoes, cargo ships, the wristwatch, wind turbines. 5 ordinary things, 5 extraordinary stories. Now revealed as we go behind the scenes, inside the machines, to find out how do they do it. Deep beneath the plains of Ontario, Canada, there lies an underground city, complete with houses and stores, its own power supply, and a road grid system large enough to rival any downtown district. Indeed, this subterranean metropolis is so big, it's even got its own gas station. The city, of course, is no city at all, but a mine, far bigger than any coal or gold mine in the world. So what are these miners looking for? Salt. This is the Sifto Salt Works in Goderich, Ontario. The plant churns out 25,000 tonnes a day. These forklift drivers never stop. Demand is huge, and for good reason. We need salt every day just to survive. Our bodies must carry 250 grams of it to help maintain our blood supply. But salt, which is made up of 2 basic chemicals, sodium and chlorine, also has a vast number of commercial applications. Indeed, salt appears in over 14,000 different products. Everything from paper to plastic, from cosmetics to chicken feed. And of course, in the brutal Canadian winter, salt keeps ice from the roads. The most common source of this miracle crystal is a 400-million-year-old mineral known as rock salt. Thankfully, rock salt is plentiful, but to get it means going a long way down. At 600 meters underground, Goderich is the deepest salt mine in the world. That's like Toronto's world-famous CN Tower pointing downwards. But Goderich is also the biggest salt mine in the world.
This is the Cadillac of mines.
The action starts at this giant airlock. It's part of a massive ventilation system. These doors are the city gates to Sifto's underground metropolis. These cavernous streets are a product of the way they dig the mine. It's known as the room and pillar method. As the salt is dug out, giant pillars of rock are left in place to support the roof. With such massive support, tunnel collapse is pretty unlikely. But smaller rock falls are still a problem. So the miners deploy this. It's a metal dinosaur, and it's the biggest machine in the mine. It's called the descaler. Its job? to scrape away every gram of loose rock and debris until it's safe for mining to proceed. Five kilometers on, deeper into the mine. The ceiling drops to just 3.5 meters. Things are about to get tight. We're approaching the sharp end of the mining operation. It's called the cutter, a kind of giant mobile chainsaw. The cutter slices 3.5 meters into solid rock. The aim, to loosen the giant slab of salt and make it ready for blasting. Charges are laid, the area cleared, excavators move in to push blasted fragments of rock towards what looks like a hungry hole in the ground. It is in fact the upper level of this giant juggernaut, a monster rock crusher. It could be a scene from Aliens, or perhaps Total Recall. The crusher mashes big lumps into smaller bite-sized chunks. It resembles moon rock. It's actually salt. Once crushed, the salt heads off into the gloom along 7 kilometers of conveyor, on a journey that will take it through more stages of crushing and sifting, and eventually to the surface. This salt is now ready for dispatch, but it's industrial, way too coarse for human consumption. To get table salt, the folks at Sifto use a different process altogether. Instead of sending people underground, they send water. These wells pump a high-pressure jet down 600 meters. The water hits the salt layer and comes back up to the surface as brine.
Yeah, it's very small and not much going on that you can see, but it is one of the most important parts of the plant. Without the brine wells, we really have no product. We have no raw material.
The brine ends up here, in a place called the vacuum evaporation plant. It's a high-tech name for a relatively simple procedure. The brine passes through a series of giant vats, each one holding 20,000 litres, where it gets super steam cleaned under vacuum pressure. Eventually, the salt ends up here. A giant rotary dryer. The temperature is phenomenal, in excess of 40 degrees centigrade. The dryer tumbles the salt until it turns from a gunk-like sludge into fine white powder. Ready for the table. It's the end of another shift at Sifto, but these miners will be back again tomorrow. As long as we need the salt, the miners will be there digging it and pumping it from the unforgiving soil. The average person in the street takes 10,000 steps in a day, which is almost 7 kilometers, depending on your stride. In one person's life, you can expect to have walked the equivalent of 4 times around the planet. During a marathon, a runner will take 30,000 steps, each one creating a force of up to 4 times their body weight. which is why running shoes are such a miniature wonder of engineering. They don't just reduce shock and impact, they're designed to prevent injury, improve balance, and can help you run for longer, better. So when it comes to putting science into footwear, how do they do it? Japanese company ASICS are at the forefront of running shoe R&D. They produce 20 million pairs a year.
This part is carved too much. It needs to be filled in here.
Their research institute of sports science in Kobe is a centre of excellence for any sport that requires shoes. Here, scientists and athletes work together to learn how biomechanics can be translated into the manufacture of a shoe. And their leading scientist is Dr. Tsuyoshi Nishiwaki, or Waki to his friends.
This is the first running shoe the company made about 50 years ago, and it only had 5 parts. These are the current shoes we're making. They consist of about 50 different parts.
Many of the features in sports shoes today are the direct result of his research. Waki believes to understand the design of a running shoe, you first have to understand the way you run, and every single step has 5 phases. A special pad on the insole of a sports shoe shows the pressure at different stages. By measuring the changes in pressure, Waki has come up with an optimum direction that the foot travels in. It's called motion guidance.
Motion guidance line is very, very important for designing the running shoes. Based on this line's position and the direction, we designed the reinforcement direction and groove direction, increasing the gripping property.
Studying how the foot works is vital for developing sports shoe designs. The perfect sole starts with rubber. The amazing thing about rubber is how versatile it is. One block can be turned into 1 million products. What's important to the sole of the sports shoe is grip, and getting the right gripping property is like cooking. These guys are, in effect, rubber chefs. Welcome to the ingredients cupboard. In this lab are different chemical compounds that are carefully weighed and added to the rubber. These give it its different qualities. Everything is thrown into a mixing machine where it's cooked and kneaded like dough. The rubber is carefully placed into metal molds, like sandwich toasters, and pushed into hot ovens to melt them into shape. It's hot work. Each section of rubber is built up to a series of molds to make a finished composite sole. Finally, the rubber sole, with all its directional patterns, textures and properties, is made. But that is just the beginning of the running shoe, and of Waki's work. Back in the research lab in Kobe, today, Waki's looking at heels. The heel takes the most impact when running. It's the foot's natural shock absorber. That's why there's so much skin and tissue there. But with 4 times the body weight of the runner pounding on the heel, that's a lot of potential damage. So, what's Waki's solution?
We inserted this intricately designed gel at this position and at this position. These gels absorb high ground reaction force in running.
The gel is so good at absorbing and dispersing energy from impact, they proudly said it could even prevent an egg breaking from 6 meters. So we put them to the test. The special gel disperses the energy of the impact outwards rather than straight down, spreading the force, not compacting it.
Okay, it's not broken.
And just to prove it's not broken, back in China, on the assembly line, this gel is glued in between 2 parts of the midsole. The completed midsole has all the gels, cushioning and support elements. It just needs the finishing touch, the moulded rubber sole. And all that's left is for the midsole to be checked and cleaned. Now the underside of the running shoe is complete. Back in Japan, Waki is looking at the way the foot moves and how that affects the upper section of the running shoe. As it lifts off the ground, the foot is at its most deformed. All the straining is on the joints around the toes. This uneven strain distribution causes the running shoe to scrunch up behind the toes. Alongside all this high-tech research, sometimes a little bit of low-tech is needed to solve problems. Creating a marbled effect will show up pattern changes in the fabric more easily. A special computer linked up to 2 cameras records the changes in pattern on the side of the running shoe. The computer shows up where the different stresses on the fabric occur as different colours, and there is a different strain on the toe to the back. What Waki has done is apply a stretchable fabric in between.
We inserted new stretching materials on here. We called it biomorphic fitting systems. These stretching materials interrupted the strain continuity from here to here.
Waki's designs all need to function in extreme conditions. This special climate-controlled chamber generates temperatures ranging from 60 degrees to -15 degrees centigrade. Right now, it's -15. This guy's running in the Arctic. The climate chamber also monitors another factor when running: sweat. The fact is, there are 250,000 sweat glands in the feet, more than any other part of the body, and excreting up to ½ a pint of moisture a day. A solution to allowing the feet to sweat is to layer lots of fabrics. And the fabrics are concentrated on the top section of the shoe, called the upper, which is the final part of the running shoe's manufacture. Layering fabrics is part of the secret of breathability. The uppers are wrapped around thousands of plastic feet, called lasts. An insole is hammered onto the bottom. Each batch of lasts is for a particular shoe size. One of these has your number on it.
It's not easy to make a shoe. By the time it's finished, it has gone through 300 pairs of hands.
The shoe is cooked over a grill and clamped around the last. The heat softens the rubber, which is then squeezed into a finished shape. Now, it may look like a running shoe, but no one's going running just yet. Not without a sole. Two conveyors bring the sole and the upper part to be glued together. Finally, the laces are tied, the running shoes are cleaned and boxed, ready to be sent around the world to where size 10 feet need them. The appetite for running shoes is voracious. US sales alone exceed $14 billion. In China, 300 pairs of hands have put together 50 separate parts and made an engineering wonder. Back in Japan, the work for the next running shoe has already begun. "90% of the world's trade is moved by ship, and that figure is growing. As demand for more and more products increases, ships need to be bigger and stronger to accommodate the growing cargoes they carry. In Korea, the solution to making larger, stronger ships has taken shipbuilding into the 21st century. So, when it comes to putting together a modern-day supercargo ship, how do they do it? On the southern tip of South Korea is the town of Okpo. This is where the world's largest industrial vessels are produced. And the way they do it is incredible. Traditionally, ships were made from the bottom up, but not here. At this shipyard, a ship is put together more like Lego. 85 separate blocks, each one weighing around 400 tons, are joined together one at a time. This is Lego for giants. The workers at the Daewoo Shipbuilding and Marine Engineering Shipyard are deservedly proud of the 40 ships they make each year, because these are the Trojans of the sea. And they don't take making them lightly. Every day starts with a workout. The blocks look like they've been cut straight through the middle with a saw, and in a way they have. But not by hand, by computer. Every new design of ship is broken down into precise and detailed three-dimensional sections, like blueprints. It's called cyber fabrication, and it makes finished individual 50-meter blocks ready to go. All you have to do is put them all together. But what happens if one steel sheet is cut a centimetre too wide, or welded in slightly the wrong position, or fitted together just out of place? The finished block will not fit the jigsaw, and that costs, well, a ship. So how do they make sure every part of the process achieves the accuracy needed for this system to work? Introducing the plasma cutters, the tailors of steel. The pattern on each plate is transmitted directly from the computer. It's mapped out on the plate first, then cut using a device a bit like a welding torch. The different sections are then given an individual number and sent on their way. Working to an exact blueprint means this is shipbuilding by numbers. In the assembly shop, if the cyber fabrication system is working, all the cut steel plates should slot exactly into place. Still, there is a little coaxing to be done. The steel slabs need to be winched tightly into place, then locked using hydraulic clamps. As they make their way down the assembly line, each section is added to bit by bit, resulting in a massive 50-metre finished block. Moving the blocks into position is down to the keen eye of the workers. Making sure they stay in position is down to the welders.
All products like oil, gas and cars are carried by ships. To make one ship takes 1 million sections of steel, all put together by welding.
Without welding, the building of a ship would not be possible. It's critical to keeping it afloat. If a breach occurred and a weld was not watertight, it could potentially sink the ship. However, there are some places that even the tiniest of welders cannot get to. Only one thing is up to the job: a robot. These are automatic welding robots. They can squeeze into spaces 1 metre square. And they get commands from the main computer. Over 1,000 control programs translate into information about type and depth of weld. As the blocks are finally assembled, man and machine work side by side. But once it's finished, how do you move a 50-metre, 400-ton block to the dockside? These transporters may look like something out of Thunderbirds, but they're the cool solution to the problem of carrying the blocks around the shipyard. Each transporter has its own safety warden cycling ahead of it to keep traffic out the way. This method of putting all the blocks together at once is only possible with a combination of precise measurement, design through cyber fabrication, and the world's largest Goliath crane. At over 120 metres high and 150 metres wide, it can lift weights up to 600 tons. It is so big that just the letters on the top are the length of a bus. Its job is to lift the assembled blocks and drop them precisely into position onto any one of the 5 ships that are being made in the dock. To get there, this lumbering giant moves 300 metres along a rail track, moving other cranes out of its way as it goes. Now the block is ready to just slot into place. However, here is the moment of reckoning. Will it fit? Have all the parts of this cyber-fabricated system been made accurately enough? And how do they fit it without leaving any gaps? Measuring the position and specific size of the ready-made block is done by using special 3D equipment. This identifies 3 coordinates on an X, Y and Z axis by locating targets placed on the block. These coordinates are fed into the computer and compared to the cyber design. The tiniest error in measurement must be corrected and the block pulled into position, even if it's just a matter of millimeters. The final gaps between the blocks are sealed by welders. And finding out whether the ship is actually watertight will have to wait for the launching. It will take 3 years to put all 85 blocks together. Only then will this ship be named, launched and sent on its way. Then another single block will take its place and start the whole process again. Time waits for no man. Sunrise. Time for work. Time for lunch. Deadlines, timelines, rush hour, drive time, night time. As the sun is setting in Asia, it's rising in the Americas. Time zones define the planet. The modern world depends completely on accurate timekeeping, so much so that it's almost become an obsession. Time measures our day and tells us where we should be. And yet, there is something we all take for granted, an incredible piece of timekeeping engineering that has been reduced to a size we can wear on our wrist. The story of the wristwatch is a tale of three seemingly impossible hurdles. Energy, how to produce enough power for the watch to work. Size, how to fit this into this. And accuracy, how to measure time itself. So, how do they do it? It turns out the best source of super accurate timekeeping is right beneath our feet: quartz. Quartz is the secret ingredient of modern timekeeping. And incredibly, it's one of the most common minerals on the planet. It makes up around 12% of the Earth's crust and is found on meteorites and moon rocks. It is everywhere. However, before it can be used in a watch, it has to be mined. This is the Sci-Tech Open Cast Quarry north of Quebec City in Canada. It processes 200,000 tons of quartzite every year. The question is, how can a common rock tell the time? Incredibly, quartz has a hidden quality that only reveals itself when under pressure. It vibrates. When compressed, it creates an electrical charge that makes it continuously oscillate, 32,000 times a second. To bring this down to watch size, the quartz is placed inside a tiny metal vacuum called an oscillator, each one the size of an ant. By doing this, the quartz can be linked to a circuit board, which is programmed to count the 32,000 pulses, then return to zero. Which means the constant vibrations made by the quartz are translated into electronic pulses, each 1 second long. And that's how a rock becomes a clock. At Seiko Epsom's Seojiri factory in Japan, the oscillator is just one of 250 tiny parts that they have to fit inside each of the watches they make. And the workers who assemble these parts have to pass through a special dust-free wind tunnel. One single speck of dust could ruin everyone's day. The assembly process involves both humans and machines. And the same interaction of man and machine is how Seiko Epson have overcome one of the greatest challenges in watchmaking: how to create a watch that generates its own electricity. What they've done is use the energy from the motion that goes on all around us to power a kinetic watch. What the kinetic watch does is capture the energy from the natural movements of the wearer's arm, amplify it, store it, and use it to power the timekeeping mechanism. They have essentially reduced a power plant to the size of a thumbnail. Unlike other watches, the designers of the kinetic watch take positive advantage of the fact that it's worn on the wrist.
The kinetic watch is unique because it only needs arm movement for power.
So, how have they done it? An oscillating wheel turns each time the arm moves. This movement is increased by 100 times through 3 cogs, which eventually reach one of the smallest elements in the watch, the rotor. This is the heart of the kinetic watch. It is just 1/4 millimeter in diameter. To produce the 1 volt of energy needed to power all the parts inside the mechanism, the rotor spins at a speed 5 times faster than a Formula 1 racing car engine. And that's how the simple movement of the arm creates energy. But what is clever about the kinetic watch is that it also saves energy, especially the part that needs more power than any other, the hands. They only need power when they move and not in between the ticks. In theory, this watch could be worn by one person from the moment they are born and never stop. It's an awesome thought. But for this to happen, it needs to be sealed for life and never exposed to the atmosphere. To make sure the watch stays sealed inside the casing, it goes through a series of rigorous tests. In a high-pressure cylinder, the watches have to withstand deep-sea depths. Then they're submerged in water to check for leaks. If water is present, drying the watch on a hot plate will reveal condensation on the glass. These watches have passed the test. Now the kinetic watch can last a lifetime and join the rest of the world's watches to mark and maintain the daily rhythms of the human race. They stand like giant sentinels against the sky. The only movement? Massive blades silently spinning, shimmering in the sun. Look around, and there are dozens of them. In some areas, there are hundreds. But look too long, and the effect becomes hypnotic, the spinning blades lazily drifting in and out of synchronized movement. But this is no bizarre piece of modern art. These are turbines. They make electricity by harnessing the power of a natural resource, the wind. So, how do they do it? The first ingredient, of course, is wind, and plenty of it. This is the Tehachapi Valley in Southern California. It's one of America's windiest spots. The reason? Geography. Tehachapi lies at the edge of the Mojave Desert. As hot air rises from the baking ground, cooler air gets drawn from the Pacific coast, some 200 kilometers away, and funneled up the valley. The process is called convection, and it's why Tehachapi is home to more than 5,000 wind turbines. Turbine engineer Michael Burns works for Oak Ridge Energy Systems, one of the dozen or so wind farms that ply for trade in Tehachapi. It's Burns' job to keep the turbines turning. And the biggest challenge he faces is one you might not expect: bugs.
The bugs deposit on the blade, on the leading edge, and when the air is supposed to follow the contour of the blade, instead of following it, staying attached. It's like it hits a speed bump, so it comes around and goes like this away from the blade, which causes it to lose lift, which is kilowatts. You turn a 750 kilowatt turbine into a 400 kilowatt turbine just from bugs on the blades.
Bugs can seriously hamper electricity production. In the Oak Ridge Energy Systems Control Centre, staff have come up with a neat solution. At the press of a button, a computer triggers this. It's a kind of giant car wash, and it's designed to keep the blades clean and bug-free. Clean of bugs, the blades can rotate up to 50 times a minute. Their job? To convert the forward movement of the wind into a circular motion and then translate that motion to the business end of the turbine, the generator. The generator is housed in a compartment called a nacelle. The only problem? It's around 60 meters off the ground. And the only way to get to it is straight up. It may seem a daunting prospect, but to Burns, it's all part of the job. At the top, the space inside the nacelle is cramped. The views across the Tehachapi Valley equally spectacular. At last, the business end of the turbine is revealed.
Okay. Main shaft, gearbox, the generator. So that lift is converted into horsepower, which is then converted into energy.
But how do all these units actually work together? At a factory in Denmark, we see the wind turbine's inner workings take shape. Once housed in the nacelle, these components can conjure electricity out of thin air.
Now we are in the nacelle of the turbine, and that is where the real magic takes place.
The main shaft runs from the blade's hub and turns a series of gears. The gears convert the blade's 50 RPM to 1,800 RPM. It's this jump that makes electricity. Back at Tehachapi. The raw current runs through these massive cables all the way down to ground level. At the tower's base, the cable's linked to a transformer. Here's where the second bit of magic occurs. The transformer bounces the electricity between two magnets of different strengths. The result? A step up in the current from 25,000 to an awesome 450,000 volts.
When the wind is up high enough and all the turbines are producing what they're supposed to, this park by itself could supply 34,000 volts.
Cables then run from the transformer and feed directly into the area grid. Like a tributary of a giant river, the wind turbine continually pours its current into the main stream. Wind farms are a relatively recent addition to the landscape of North America, but they're set to become a very familiar feature. And that's good news for Tehachapi. The community stands poised to benefit from an energy bonanza, harvesting what is today an increasingly valuable resource. They've got plenty of it, and it isn't about to run out.